So my name is Andy Nicholls. I'm the head of conversions at S Jones Containers. We have been specialising in engineering processes in containers for many years now, and in a variety of different industries, including automotive, water treatment and energy. In particular, S Jones have been manufacturing battery storage and testing units for 6 to 7 years now. One of the difficulties we find is that customers have no guidance. So they don't know what is required when storing the units, how far away from the building, how much human interaction is going to be in the unit, and what different chemical makeups. There are many, many questions. We have been working with companies like Warwick Manufacturing Group and Warwick University and the Fire Protection Association to understand the behaviour of batteries and the safe practices when dealing with them. Because of this, we have been able to offer with confidence a full range of containers for storage or testing, including features such as fire suppression, gas detection and many more. However, budget of customer varies. This means we must then use our experience to provide the safest possible solutions based on budget rather than safety. We also tell our customers we can guide and give you the tools, however, insurance and risk is down to them to evaluate. Today, I'm pleased to be joined by two professionals that have knowledge to share with you that is worth its weight in gold. First, we have Dr. Simon Jones from Warwick Manufacturing Group and the University of Warwick. Simon's experience in battery R&D is second to none, and working with him at Warwick has helped us develop a truly safe system for storing and testing batteries, as he has studied the behaviour of them for so many years through testing. Final speaker today is George Edwards, Technical Director from the Fire Protection Association. George and his team have produced many guidance documents such as need-to-know guides for battery use and storage. Thankfully, organisations like the FPA are out there to provide companies with advice. So I'd like to hand over to Simon Jones to start off today's panel session.
Hi everybody, I'm Simon Jones. I am Chief Engineer of the Energy Innovation Centre at WMG, which is an academic department at Warwick University, but we're very heavily focused on working with industry. And my role is to provide a testing service and sort of expert advice to industry on battery safety and battery characterisation and all kinds of battery testing. Going the wrong way, there we go. So what I'm mainly talking about today is battery safety testing, also known as abuse testing. And of course, a lot of people in battery world aren't aware of the need for battery safety testing. So I often find myself asking the question, why are we doing this again? There's a lot of reasons. Battery suppliers, cell suppliers will give you a data sheet, and they try and put as little as possible information as they can on the data sheet. They're very minimal documents. I come from a chemistry background in materials, and I'm used to having data sheets that are sort of that thick. And then with a cell data sheet is quite often one page. So it doesn't tell you very much. So it won't tell you the failure behaviours. And this graphic here is a very simple one. Basically, the green block shows you what's covered by the data sheet. We know that if we go into abuse conditions, that's the red box, that's where you're going to have a failure of some kind, possibly a dramatic one. There's also the area in the middle, which is an excursion from what the manufacturer says you're allowed to do, but it may or may not be okay. So a lot of the work we do is focused in that area. It's finding out what happens if this happens. And of course, if you're designing a battery pack, you want to know whether those excursions are going to result in a disaster, whether they're going to result in you having to scrap the pack, or whether, providing you keep it within certain limits, it will be perfectly okay. A lot of what we do these days as well is to provide data for programming of battery management systems and for modelling, because this world is moving more and more towards modelling as fast as we can. But the ultimate reason we do safety testing is to make a safe battery. We accept that you can never guarantee that you won't have a single cell event within a battery pack, but we want to help people design battery packs that are inherently safe. So in other words, even when you do get a single cell event, it's not a propagation. And then we have a safe pack. So, what are we working with at Warwick Manufacturing Group? We have 7 abuse chambers, so that these are safe spaces where we can carry out reasonably scaled battery tests. They're fire rated, they've got overpressure protection in case we have a vapor cloud explosion. We've obviously got gas detection. One important point these days is it's important to control your emissions. We've always been doing that because our abuse facility is in the centre of a university campus. So all of our gases are sucked up a chimney and go through a wet scrubber, so they're safe to release to atmosphere. Many people in the industry don't do that, and I think we have to recognise as an industry we can't keep burning stuff in fields. The most important part of our facility is data. So what we describe that as being data rich. In other words, if we're going to carry out an expensive and hazardous experiment, we're going to make sure we get all the data we possibly can from it, which will be of value to our partners or get published in our research or whatever. So obviously temperature, obviously gas measurements, mass spectrometer, FTIR. More recently, we've started measuring chamber pressure because we want to know how big the bangs are. And being able to quantify how serious an event is actually harder than it sounds. Historically, people have often looked at a video and gone, "Ooh, that's a big one. That looks better than this one." There's very few numbers. And one thing I always say to people is don't trust the thermocouples. I've been measuring temperatures for 35 years, and the more I measure temperature, the less I believe what I see. Thermocouples are very, very useful, very easy to use, and also very unreliable. So in some ways, the other measurements are actually more valuable. So getting into the nuts and bolts of it a bit deeper. As I said, as this industry evolves, I think we need to be focusing more on the science, less on the did it pass or did it not pass, whatever pass means, but actually getting good quality data and doing the science. Warwick Manufacturing Group have been doing this for 15 years. We were one of the first people to start battery abuse testing, first I know of in the UK, but very early worldwide as well. Our speciality is doing method development, so we don't do certification testing. We want to do tests that are difficult for people that they can't do somewhere else, and we want it to be cutting edge science because we want to expand the boundary of what we know. One of the things we do, which is what's shown on this slide, is in-cell temperature and pressure measurements. So this is where we take a standard cell off the market. We don't build it from scratch, although we can do that, but in this case we take a standard cell off the market and we actually insert the instrumentation into the cell, which is quite difficult to do. It's certainly very dangerous to do, but we've developed techniques for doing it that are safe and also that don't affect the operation of the battery. So we can insert the instrumentation and we can then cycle the battery and it performs exactly as it did before. So we can then pick up data from normal operation, but we can also pick up data from what happens in abuse testing. And that's really useful because the data you get from the outside of the cell, voltage and a poor temperature measurement is not actually that useful. If you know what the temperature is in the core of the cell, and you know what the pressure is in the core of the cell, and recently we've also started measuring the gas composition within the cell during events, you actually know what is happening, and you know what is happening much sooner and in greater detail. So this is the kind of thing we love to do because it's cutting edge and it's proper science. It can be published, and we love to publish things, but also we're giving our partners information that they can't get anywhere else. Okay, so I'm going to show you a typical test. An awful lot of what we do is, as I said before, trying to stop batteries from propagating. So this is 4 80 amp hour pouch cells. They're in 2 pairs, and there's a thermal barrier between the 2 pairs. And the purpose of the experiment is really to see how long does it take from a thermal runaway in one pair of cells to propagate to the other pair of cells. And it's a very typical experiment in the automotive industry. This particular one is only 4 cells. It's part of a ramp up where eventually we'll be testing 72 cells. We've got as far as 10, but we like to be extremely careful. I'm responsible for the risk assessments, and I don't want to destroy the abuse chamber and lose my job, so we build it up as gradually as we can. So what I was just talking about there was preventing propagation, in other words, making inherently safe battery packs. I'm going to talk briefly about another failure mode, which is sidewall rupture. And sidewall rupture is particularly important for cylindrical cells, which are still used in aerospace. Quite rarely used in automotive now, but they're still used very heavily in aerospace. Most aerospace packs that are being developed are based on cylindrical cells. Sidewall rupture is when the cell, rather than venting normally through the top cap, the vent cap, it will split on the sidewall, and it will then, you'll get a very hot jet of gas and debris directed straight onto the cells around it. And as you would expect, that leads to very, very rapid propagation. So you'll, rather than have a propagation rate of maybe 1 every 10 seconds, 20 seconds, 30 seconds, it will be a fraction of a second from cell to cell. And in an aircraft pack, what that means is, because you need to contain the event, if you have a battery pack on an aircraft, you need to make absolutely sure that hot gases and debris only goes out of the designated vent. It doesn't go out anywhere else, because otherwise you'll be damaging the airframe, bringing the aircraft down. The greater the rate of propagation, the greater the temperature and the pressure inside your container, and therefore the heavier and more durable that container is going to have to be. And if you can slow the rate of propagation right down, then you can actually get away with it. But you have to make it as slow as you possibly can, preferably keeping it to a single cell. But the standards require you to make sure that you also test, assuming that you fail to keep it to a single cell. So we did a lot of work making sure that we could reliably get sidewall rupture, because, as probably many of you know, abuse tests are incredibly variable. You run the test 10 times, you get 10 different results, 2 of which will probably be wild outliers. Because sidewall rupture is one of these outlier events, it's very difficult to study. So we actually spent several months figuring out how to get a reliable and repeatable sidewall rupture every time, because we couldn't really study it until we did that. And as I said earlier, a lot of what we do is about method development, figuring out how we can do a really useful, repeatable, scientifically accurate test that we can then gain something from. And then we go about preventing it. You know, how do we make sure that the pack can withstand that sidewall rupture event? And we've introduced various materials. There's a fair bit of stuff in the literature about this already. NASA have done some work on it. Rolls-Royce have done some work on it that we were involved in. So there's some IP protection already. So we needed to make sure we worked outside the IP protection. And we did work with some foams, a variety of different density foams, and we also tested some sleeves. What we found is that sleeves are actually capable of giving a very good level of protection against sidewall rupture. There's obviously a weight penalty, and they're relatively expensive, but you can do it. And for aerospace, that is what you need to do. The foam is not quite as good. We found that it's lighter, but it's not as reliable. And I think that I would like to work more with foam. I would recommend foam to people, but I wouldn't promise anything to them with the foam. I think more work is needed. So in terms of what we do going forward, and the kind of facility that people need to do testing, one thing that's really been really obvious to us for about the last 4 or 5 years is that cells are getting bigger. I mean, this is no secret, everyone knows this. Less the case in aerospace for some particular reasons, but in automotive certainly. And if you think about people like Fortescue, who are building big earth-moving, big mining equipment, the cells get really, really large. So we've gone from sort of 4 amp hour cells to anything. I've certainly seen them in the 300 amp hour range. And of course, they're an awful lot more hazardous now. So you can't do the testing in the same way you used to do it. We and also other people working in the field need large-scale capability. We are aiming to get a national facility, a bit like the one at Rise in Sweden. We think that that's what the UK needs, but as you all know, there's very little government money around at the moment. So probably the £100 million we would need to have a really good national facility for battery safety testing. That's just not there, unfortunately. So we'll have to make do for the time being. We have put a lot of effort into thinking about what we can do in our facility within our budget, and we've looked at what we need to protect against. And probably the first thing to mention is overpressure. You don't always see this when you're doing an abuse test. In fact, dangerously, you very often don't. You might be able to do 100, 200 tests before something like this happens, and therefore it tends to take people by surprise. It became sort of better known about 2 years ago. Before that, people didn't really talk about it or explain it in the literature, but the vapor cloud explosion or deflagration is when the cell doesn't burn initially, so the gases that are given off fill the room or form a cloud around the item, and then later it's ignited. And it might be ignited by someone opening a door and increasing the oxygen content, or it might be ignited by a spark. This can be extremely dangerous. So in our abuse chambers, it could actually potentially destroy them because they're not engineered for this yet. That shipping container at the bottom is an example of what can happen. Even a few hundred millibar overpressure, which to most engineers, mechanical engineer like me originally, that sounds like a trivial pressure. But trust me, in blast, it's not. A couple hundred millibar will kill people and push structures over, and you can easily achieve that with a vapor cloud explosion, and it's pure luck. It's very, very random. So blast pressure very much needs to be considered. Fire is far less controversial. Of course we know there's going to be a fire. Everyone's experienced these, anyone who's done the testing, and the state of the art in fire protection can easily cope with the fire resistances needed. Although they are hot fires, but they are reasonably conventional fires. And then I've already talked quite a lot about emissions, but you can see there a picture of our chimney stacks. That's post-scrubbing, and I do get a lot of people saying to me, it's still smoking, why is it still smoking? And to be honest, it's steam. It's mostly steam once it's been through the scrubber. But we do use an FTIR machine to measure what's coming out so that we know it's safe, and I think that's the kind of level the industry needs to be operating at. So we need to know what we're putting into the atmosphere. So we're in the process of specifying and building a new safety centre, which I'm hoping to have operational April next year. May well end up being a little bit late, but we have the funding, we have the site, we've specified some of the equipment, so that will be going in. And this is very much focused on that being able to do the large-scale testing. Big cells, 300, 400 amp hour cells in large clusters. And that's because that's what industry needs. The researchers are quite happy to continue working with small cells, but I'm not, because I know our partners need the ability to do large-scale testing. So our new facility is going to be made up of these converted shipping containers. We're going to have 3 test chambers. We're going to have a very large, powerful scrubber. The features of the containers, blast panels, so we can cope with the overpressure. Obviously, the blast panels are about this big, well over a metre square. And the fact is, if you don't have that kind of opening, you're going to end up blowing the doors off your chamber or deforming the walls of your container. So you need large blast panels, and they also need to be very fast reacting. We'll be measuring overpressure. Obviously, we'll have gas alarms, water mist, fire suppression, and also another big upgrade is we're going to be having FTIR and oxygen and hydrogen sensors in every chamber, so that we can measure the emissions from every single test. Gas measurement has been something that's been done quite poorly in the past. It's quite difficult to do well. We're determined to get to the point where we get good data off every single test. That FTIR or another FTIR will also be measuring the stack emissions 24/7. So the vision we've got, data rich, as I mentioned earlier, large cell format capable, and that's because we want to be able to give industry, our partners, really accurate data of how severe events are. And if we can characterise how severe each event is, we can actually get much, much better at being able to prevent events, because we understand whether an event is a 9 out of 10 or a 3 out of 10. At the moment, it's incredibly subjective. You need to be doing really good data collection to be able to make that distinction. That's what we're determined to do. Okay, that's all I've got, so I'm going to hand over to George.
Well, thank you very much, Simon. I think Simon gets to talk about the interesting bit about setting fire to batteries and showing some videos of them. I've got the boring job of telling you what you should and shouldn't do. I think it's always a challenge when you get test data and things like overpressure values and temperatures, but how do we actually turn that into sort of meaningful guidance that we can use in the real world? And I think that's always the difficulty. Just want to start by going through some recent fires with batteries, just to put a bit of perspective on it all. So there was a fire in May in Bristol. This was an e-scooter fire, top story of a building, and 2 people were treated by the ambulance on site, but everybody did get out, so it wasn't a disaster, that one. Back in April, there was a large fire at a Scottish battery recycling centre. Quite a really significant fire, a lot of huge flames, a lot of smoke, toxic smoke coming off, and the houses in the surrounding area were evacuated. Fire service had to go in with hazmat suits on. So these are the sort of real world problems that you can have, which Simon's experienced at his facility. Obviously they've got the advantage of staying remote and venting it all off, but in the real world people have to and sort of deal with those things. And then back in March, another e-scooter fire in a flat. This one blew through one of the internal walls, and the residents had to jump for safety from the flat. So there are some big problems with these, particularly e-scooters. We do see a lot of those, and that generally tends to be an e-scooter that's had the battery changed or had some modifications to it, or not the original charger. Those are very common things that we see whenever we look at real-world e-scooter fires. So, going to talk about the guidance next, and a little bit about Risk Authority first, who's produced that guidance. So, Risk Authority is a research scheme for the insurance industry, and we basically gather up data from various insurers, form together sort of working groups, different experts on, and produce guidance. And you might be wondering why insurers would want to produce guidance for the public, because all of these guides are freely available on our website. And the reason is because, at the end of the day, they're the ones insuring the facilities, they're the ones insuring the cars, the scooters, the houses, and they want to reduce the number of fires. So they put out best practice guidance out there to try and reduce these events for their benefit and for your benefit. So we've got 4 main guides at the moment on lithium, or related to lithium-ion batteries. We've got one sort of on the recommendations for charging electric vehicles. We've got one on secondary batteries and associated hazards. A secondary battery is a rechargeable battery. And then we've got these 2 sort of need-to-know guides, and these are very popular. They're sort of very compact, short guides, a couple of pages long. They just sort of tell you all of the key things that you need to know about that. And the general structure of these guides, they'll go through what the main hazards are that have been identified. Then they'll talk about some recommendations for dealing with those hazards on your site. They'll have a checklist or a questionnaire, and that's useful if you're sort of designing a site or a facility, or if you're doing a risk assessment. You can go through that checklist or questionnaire to cover everything off. And they're also useful for the insurers, so they can go to a site and go, okay, cool, these points are covered off. We're happy with that. We can offer lower insurance or whatever. And then we always include our references at the end, or resources, links to sort of further research for yourself. And the last bit, and a lot of this is sort of, best practice based on general fire engineering principles. And then it's sort of these 6 things here that really can apply to any hazard. So the first one is preventing the hazard. What can we do to prevent that battery from starting in the first place? The next one is detecting the hazard. What's the earliest, cheapest way of detecting that hazard and most reliable? Then it's suppression. How quickly can we get water or an extinguishing agent on there? Then it's compartmentation. So if that suppression's failed, or it's just controlling it a little bit, we want to try and keep that fire in a compartment, and whether that's the battery inside the battery housing unit, whether it's inside a fire compartment inside a building, how can we contain that fire so it doesn't spread to the rest of the facility? If compartmentation fails, then evacuation's the next thing. We need to get everybody out of the building as soon as possible. And then the last one is damage resistance, which is making sure that the rest of the facility, building structure, is well resistant to damage and resilient in case one component fails, that the rest of it isn't all going to fail as well. So I'll go through some of those in a bit more detail. So we've got RC59, which is our recommendations for charging electric vehicles. And charging seen as the sort of highest risk activity for electric vehicles. And it becomes a lot more risky when it's in enclosed or poorly ventilated spaces, underground car parks, things like that can be particularly dangerous. And that's because these gases can build up, and then you've got that high risk of a vapour cloud explosion. And so you do really want good ventilation in those areas to try and reduce the risk of those vapour clouds building up. Now, a lot of these are sort of very simple points, and it's all about just collecting them all up together in one place in some guidance, so that you can have a look at it, go through, and make sure you've got all of those sorted on your site or wherever you are. So designated charging zones should be clearly well marked, which again, very simple, but having a designated charging zone means you can control everything around it. So you can make sure there aren't combustibles around the area, there aren't things that you're worried about the lithium-ion car setting fire to. And you can also control things like having bespoke detection there that's bespoke for electric vehicles, and suppression as well that might be bespoke for electric vehicles as well. Your charging infrastructure, that should be certified and installed by qualified professionals. And vehicle spacing is quite important, particularly as cars are getting bigger. The fuel loads, even in general combustion engines, there are a lot more plastic around the cars and things as well, and the same for electric vehicles, same trend, so bigger spaces are needed. You need to have emergency plans on site and specific ones for your electric vehicles. So for those fire scenarios, what are the fire service going to do on site? Some fire service are not putting water on electric vehicles because although that can reduce the heat and reduce additional flaming, it can increase the chance of an explosion, because basically you're not going to stop the off-gassing, so the gases are still going to build up, and then one spark and suddenly you've got an explosion. So some fire services are not putting water on, and then that's something you need to be prepared for on your site. If that's a decision they're going to make and go in and not put water on, you need to be prepared for that for the rest of the facility. Regular maintenance and inspection of your charging points. Like I say, charging is one of the biggest risks, and particularly with cables, we're seeing a lot of replacement parts and replacement cables. Everybody does it with their phone, where you don't buy the original manufacturer's cable to charge your phone with. Most people in this room probably use someone else's cable, and we're seeing that on a large scale with cars as well. And the last one is public education. And that's key, and we've got some steps in there for that, but I think that's one of the main things, is making sure everybody's aware of the hazards, and that's really key for a lot of fire hazards, is just making sure everybody's aware. So next guide I'm going to talk about is RC61. Now this is an older guide on secondary batteries, so rechargeable batteries. So this covers all sorts of batteries: lead acid, sodium ion, redox, solid state, as well as your lithium-ion batteries. And you can get similar hazards with those that we hear a lot with lithium-ion, things like thermal runaway. That's still a risk with your older batteries. Lead acid ones can actually produce large amounts of hydrogen gas. And in lots of scenarios, people are prepared for that these days. You will have a lead acid battery in your car and your typical combustion engine, but that's in an area where it can ventilate off and not cause a big problem. But in some places, if they're contained, they're in an area where they can start overheating, start off-gassing, producing hydrogen. Suddenly you've got a risk of a big hydrogen explosion, which can be really fatal. So it's important to make sure we don't forget the lessons of the past with the older batteries, which are in place in a lot of areas, but people are starting to forget them. And the same with toxic inflammable gases. Big issues for all types. Electric shocks, these are high voltage systems, a lot of stranded energy there, and that environmental risks as well, with sort of not just toxic gases, but also the toxic materials for these and the disposal of them. Lithium-ion batteries in particular, they can, after a fire event, they can still reignite hours after the event when you think it's safe, days after the event. I've seen them do it 3 weeks after an event, and that was at a facility where they had some cars. They'd set fire to them, they put them in their sort of scrapyard car facility, thought it was all safe. 3 weeks later, that caught fire, set fire to the whole thing. And the record is actually 9 months after an event that a vehicle caught fire. So yeah, it is a big hazard there. Like I said, this was an older guide, but we do update it, and we have included a section specific for lithium-ion batteries to talk about the additional hazards there, higher density, more prone to thermal runaway, very complex fire control, as I talked about, risk of explosions and things, and I'm sure Simon knows a lot more about this than me. And then the criticality of battery management systems, and these can be really effective at controlling it, making sure that a thermal runaway event doesn't start. And I'm sure Simon's had lots of challenges with battery management systems about setting fire to lithium-ion batteries, because one of the things when you do fire testing is making sure that system doesn't prevent you from starting the fire that you want to, and they can be very good or very frustrating if you're trying to set fire to them. So, and then general fire safety tips, I say, use original chargers, avoid damage, don't overcharge. All sounds like simple stuff, but it's the main cause of fires that we're seeing with these. Store it in cool, dry, ventilated areas, flammable materials, and dispose of damaged batteries safely. Don't just assume they're going to be safe. Now, the need-to-know guides, like I say, these are a lot more popular, it's a lot simpler. And the first one to talk about is on battery energy storage systems. So these are your large-scale battery energy storage, typically in large containers, and there can be big sort of fields full of them. One of the key things is about the location for them. Make sure the enclosure is designed to reduce the risk of explosions and also contain what it can. So Simon was talking about overpressure vents earlier, and again that's one of the key things here. But also, ventilation and venting is absolutely key, and you can have detection systems that enable early ventilation in these, because that's really what you do is stop these gases building up, and then you can reduce an explosion event. System maintenance, really important, and that's stressed a lot throughout our guides, because if things are well maintained and looked after, we're seeing way less risk of these events happening in the first place. Risk assessments are a big part of that as well. They can spot things like poor maintenance, but also just risk assessing around the site, container spacing, things like that, making sure that the vents are all operational, and all the necessary checks are being done. Emergency response planning, and that's key for these, and that's planning for your response on site, but also firefighters when they come to the site, what are they going to do? And you can do things like have containers that you can remove from all the other containers, so sort of salvage those ones, or salvage the healthy containers around it and make sure they're moved out the way, so it's all contained to one thing. And we align a lot of stuff with standards like NFPA 855 for stationary energy storage systems. And the last guide I'm going to talk about, and there's no more guides after this, is our need-to-know guide on lithium-ion battery use and storage, and it's the most popular one that we have. As I said many times, charging is the riskiest time, especially if your battery is damaged, faulty, or got replacement components. Fires can spread really rapidly, releasing these toxic smoke and gases. Enclosed areas, car parks, indoor spaces, massively increase the danger, and that's, like I say, because of this build-up of vapour clouds. So you do want to make sure you're using safe, certified charging equipment, so from the original manufacturer. Don't use DIY stuff or modified chargers like yourself, unless you're doing fire testing. Charge it in well-ventilated areas. Don't leave your EVs charging unattended for long periods. Keep your charging zones clear of flammable materials, and report any damage to charging points or cables immediately. So, bit of a summary, and this is a graph from one of our guides, which talks about really sort of how dealing with the hazard earlier on, the earlier you deal with it, the more effective your control can be. But like I say, it's really important that you take a lot of care when charging. Batteries stored safely. Cool, dry, ventilated areas, away from flammable materials. Avoid damage to them. Any signs of being crushed, punctured, or exposure to these can set them off. You can set fire to a phone really, really easily. Just with a small puncture, it's quite scary to see. Make sure you're using certified products, disposing of these things safely, and only trained personnel should be handling these battery fires. You don't want to be doing this on your own. And that's one that's really, really important to stress. Like I say, these things can gas off, and if you've seen one or two of them, you might be like, oh, okay, right, that's going to turn into a fire, and that's cool. But in other scenarios, that gas can just explode. And yeah, you need a lot of experience to know what you're doing in those scenarios, because if you're not experienced, you're going to go in thinking it's safe, and then it's just going to explode on you, and you're going to be severely burnt in the best case scenario. So those are the guides that we produce, but there are lots of other resources you can look at. Stuff from Massachusetts. There's some FM Global guides. FM's a big insurer in the US who do a lot of fire testing. Fire Industry Association's got some, and Euroalarm as well. And the last thing I want to talk about is a product regulation and metrology bill. So this is very exciting. But yeah, there was a lithium-ion battery safety bill that was brought in a couple of years ago. Well, it was proposed a couple of years ago, and that's basically not gone forward. That's going to be included in the product regulation and metrology bill, which is in the final stages. And this basically will give the UK more powers to regulate lithium-ion batteries, e-scooters, bikes, consumer electronics and chargers, and making sure that we're getting in safe products into the UK. And it'll give us stricter regulations around third-party assessments for these, improved labelling and consumer guidelines, so that consumers know what they're getting, and people can vote with their wallets and buy proper products. And also some public awareness campaigns on safe charging and storage. So that's hopefully gonna help in the area, and something that's been called for a very, very long time. So that's everything from me and everything from us. So yeah, thank you very much.